Good evening. Today we shall have a continuation of the talk that we had 2 weeks ago. Gosha, you're
Yes.
welcome.
Well, I wouldn't say that it's the direct continuation. I cannot tell what it is. There are some direct consequences. There are some direct consequences of what I was speaking about 2 weeks ago, but I'll try to draw some bridges between what I told you 2 weeks ago and what I'm going to tell you today. In the very end of my talk, if I have time, I'll try to draw some bridges. But most part of my talk will be totally, well, departed from what I was talking about last time. So my talk today is about the quantization of the so-called argument shift method. Let me recall you the conditions, the initial points of this instruction. Let M, comma pi be a Poisson manifold here. Pi is an arbitrary, is a bivector which verifies the Poisson identity. Such bivectors are called Poisson bivectors. The Poisson identity means that the Schouten bracket of pi with itself vanishes identically. This is the Schouten 9th bracket. In this case, as one knows, one can define the Poisson bracket structure on the space of functions on M. That is, for every pair of smooth functions f and g on M, we define their Poisson bracket by the formula. A very simple formula indeed. We take the bivector pi and take two covectors, differential of f and differential of g. There is a natural pairing between vectors and covectors, so we use this pairing to define this function. So this function is a smooth function depending on f and g. Of course, this pairing which sends f and g to their Poisson bracket is Q symmetric. It verifies, it satisfies the Leibniz rule in an evident way. That's just because the differential of g or differential of f both verify they satisfy this Leibniz rule. Sorry. And which is important, the most important thing, it is that this bracket satisfies the Jacobi identity. This Jacobi identity is guaranteed by the condition that the Schouten bracket of pi with itself vanishes. When we have such a Poisson structure, we can ask what are commutative subalgebras in C infinity of M. Well, I say commutative, of course, C infinity of M is commutative as the associative algebra, but in this case, commutativity means commutativity with respect to the bracket. And so I can ask what are sets of functions f and g such that their Poisson bracket vanish identically. So that's what we call Poisson commutativity. So the first thing to do is to describe the Poisson center of this algebra. That is the space of all functions which commute with everything. The Poisson center in this case is just the space of all functions for which the Poisson bracket vanish for all G. If, well, roughly speaking, well, not even roughly, but speaking geometrically, let's put it this way, geometrically speaking, F is in center means that the Hamilton vector field of F vanishes identically. This Hamilton vector field is just the vector field you obtain by raising the indices of the differential of F by pi. We see immediately that if pi is in fact non-degenerate Poisson structure,
do you need to raise indices?
because df is
No, it's pi is by f. If you substitute a form,
well, that's what they call raising.
vector.
I think that's what they call raising indices, in my opinion. Because when you have a tensor with two upper indices, you contract it with a tensor with lower index, you get, and that's what they call raising indices, I believe. Just the definition. So if pi is invertible, if pi comes from some symplectic structure, then of course there is no Poisson center. But in general, there can be more commutative families than just what is given by central elements. Casimir elements are just a small portion of commutative families on Poisson manifolds. There can be Poisson commutative families even when you work on symplectic manifolds, and then there is no center at all. However, in the presence of center, one can use this center to produce more commutative families just by some easy procedure. Let me describe such procedure. It's what they sometimes call the bi-Hamiltonian structure. The construction, but I don't know, it's sometimes called Lenard-Magri induction, but I'm not going to speak about induction. Induction is a very particular case of what I'm going to talk about. Or one can say that what I'm going to talk about is a very particular case of this general Lenard-Magri construction. So let us suppose that there are two Poisson structures, two Poisson bivectors on M. One say that they are compatible if their Poisson bracket vanish. And equivalently, they are compatible if and only if the linear combination of these two vectors, these two bivectors, or convex combination of these two bivectors, defines Poisson structure for all t. Actually, I can erase this here or this here and just leave just one t here. It's probably more convenient. In this case, there is a very nice and simple way to speak about Poisson commutative families. Namely, one can associate a Poisson commutative family of non-central elements to any pair of this sort. It will be larger or smaller depending on what pair of Poisson bivectors you choose, but in any case, it will exist. The construction is very simple. Consider the corresponding Poisson bracket, which I'll denote by brackets with subscript t. And roughly speaking, it is equal to the linear combination of f, g with respect to the first Poisson structure plus t times f, g with respect to the second Poisson structure. This is a one parameter family of Poisson structures. Then the following is true. Claim that z sub t of c infinity of m be the Poisson center of this bracket. Then, for all t1, t2, and for all f in z t1, g in z t2, and actually for all t3, but I don't want to use them, the Poisson bracket of f and g with respect to any t actually vanishes. The proof is pretty elementary. And can be just one line proof. Therefore, I'm going to give it right now. One line proof. If well, consider, okay, sorry. Yeah, it's evident, but let me just write it down for everyone. It's evident, yeah. Let h of t be the bracket of f and g. It is a linear, with respect to t. It is a linear function in t. Hence, on the other hand, h of t1 is equal to h of t2 is equal to 0. And hence, h should be identically equal to 0 for all t. It's just because every linear function which has two zeros should vanish identically. That proves the statement. And it allows us to consider a pretty large, well, potentially large space of Poisson commutative functions. Namely, I'll call A of this pi1, pi2 be the union or sum or whatever you can call it of the centers of the algebra denoted by these centers for all t. Here's an example. Let psi be a vector field. On M, such that the Lie derivative of pi respect to psi. Yeah, I forgot to say that M pi is the Poisson structure, Poisson manifold, which we began with. Let us assume that the Lie derivative of pi with respect to psi is non-zero, but the derivative of pi sub psi with respect to psi vanishes. Then the following is true. Pi and pi sub psi verify this compatibility condition. In fact, pi sub psi is a Poisson bivector itself. So we can use this construction, applying it to both pi to pi to the pair pi sub psi. The proof is pretty simple again. When it is something simple, I prefer to give it. So we consider the equation L. We use the Lie derivative and apply it to the equation that the Poisson bracket of pi with itself vanishes identically. We get 0 on one hand. On the other hand, we get twice pi sub psi. Okay. So we see that whatever these two brackets, these two bivectors be, they're compatible.
You also need to prove that the second quality.
Yes.
No, that pi psi is a Poisson structure.
Yes, I'm going to do this
okay.
right now. I just take this, and now I have that this is equal to 0, and I apply psi to this equation.
Again.
I get 0, but on the other hand, I get pi psi plus pi L psi pi psi. So the second term vanishes by assumption, and I get what I promised. So we have these two conditions, they hold, and I can use these two conditions to construct the commutative family. One can actually ask what are the centers of pi sub t in this case. It's actually not very hard to see that they are generated by the following set of elements. Let f be arbitrary function in the Poisson center of pi, then z pi, this union a pi psi is actually generated by the Lie derivatives of f of arbitrary degree for all k. It's well, in general, it's not hard to see, but it is even more evident when you take a very particular example, which I am going to concentrate on.
It is obvious that any such an element lies in the center, but how to prove the opposite, that any?
Well, actually, I'm not going to prove this in general, but I didn't say that it is just this. I say that these are generated by these elements. They are generated by such elements. So let me try. I'm going to try to prove this in a very particular case. Let M be equal to the dual space of Lie algebra, right? And let psi be a constant vector field on G star. Since the standard Poisson bracket on M, which is given by the formula I wrote before, X, which you pair with the differentials of F and G at X, is linear with respect to the standard coordinates on G star, right? It is linear. Hence, constant field satisfies this condition. Now, when we have this, it is easy to see that the bracket, which corresponds to pi plus t times pi sub psi, is actually given by the following construction. You take the shifting procedure, you take the shift of f. When I write f sub t of x, I mean that I take f and substitute x plus t times psi instead of x, right? So first take ft, then take gt, and then you take the inverse, whatever it means. I mean, here you have some function of x, right? And you then substitute in this minus x minus t sub psi into this function. So that's what you get here. That's what that's the bracket you have. Okay. It follows directly that the Poisson center of the shifted bivector is equal to the Poisson center, to the shifted Poisson center of the original bivector pi. So when you have the shifting, you can actually, especially when you work with polynomial functions rather than with arbitrary C-infinity functions, the shifting f t of x is given by a finite sum of the following form. It's f of x plus t df d psi of x plus t squared divided by 2 d squared f d psi squared of x and so on, right?
By df d psi you mean
Directional.
psi of f, yes?
It's directional derivative. Directional, yeah, it's psi of f. You can call it like this. But it's psi is just a constant vector. I told you that psi is a constant vector field. So it's just the vector on G star. Hence, the center Z, whatever, A phi sub psi is generated by, in this case, it's evident. By these partial derivatives, dk of f d psi to the power k, which is the same psi times k of f, as I promised. So in this case, it's evident. In general case, you need to work a little bit more. But in fact, you can prove by mere induction it is always the case. So that's the geometric side of the story. Now I'm going to pass from geometry to pure algebra. And to do this, and to make sure that this, to convince you that this algebra is actually worth looking at, let me prove the following very simple but interesting claim. Let V be a vector space with a bilinear operation B capital V cross V to V, a bilinear operation of any sort. Actually, I think that it is even possible to consider something non-linear, but it's not. It would be too much to ask for. So any bilinear operation. Let me recall that the left and right centers of B capital are the spaces which contain all elements x of V, for which the left multiplication by x or the right multiplication of x vanish identically. Let now psi be any map, a linear map from V to V. Then the claim is as follows. For every x in left center of B, for every y in right center of B, for every non-negative integers p and q, the p-fold application of psi to x and q-fold iteration of psi to y will commute with respect to B. So it's pure algebraic story. The proof can be done by induction on P and Q. Let me make a couple of steps of this inductive process. We begin with the identity. Oh, I forgot to say one condition, very important condition, which actually imitates the condition I imposed on psi, right? I had this condition that lambda sub psi of pi is non-zero, but lambda sub psi of pi should vanish. I had this condition, but now this condition translates into the following equation. So first I take psi of B of AB minus B of psi of A, B minus B of A psi of B. And I call this B sub psi of AB. And this need not be 0. But then I take psi of B sub psi of AB, subtract B sub psi, of psi of A, B, and B sub psi of A psi of B. And now this should be equal to 0. So this is the condition which actually replaces this one. This is a pure algebraic condition, and now I'm going to use this condition to derive this kind of fact. The derivation is pretty simple. We begin with the identity b of x and y is equal to 0. Because x is in the left center, y is in the right center, so this should be 0, actually, for more than one reason. I use this construction here. B sub psi of x and y is equal to psi of b of AB minus b of psi of, a xy of xy minus b of x psi of y. Now every term here is equal to 0. The first one is equal to 0 for this reason. The second one is equal to 0 because y is in the right center. And the last one is equal to 0 because x is in the left center. So this is equal to 0. I have this. Then I consider the next construction. I take b of psi of x, y, and again do the same trick here. I apply psi to it, subtract b of psi squared of x, y, and subtract b of psi x, psi y. Now what I have here is called b sub psi of psi x, y. But all the terms on the right-hand side vanish for except one, vanish for different reasons. The first term vanish because what we have in the parentheses is 0. The second term vanishes because y is in the right center. So I see that this expression is up to the sign equal to this pairing. Similarly, b sub psi of x psi of y is equal to minus b of psi x psi y. And finally, I'm applying the same trick to the expression I had before. I had this equality, this equation, and I apply psi to this right-hand side. What I get is psi of b sub psi of xy minus b sub psi of x y minus b sub psi of x psi of y. By condition, this should be equal to 0. By condition here, this expression vanishes. On the other hand, the first term vanishes because what I have in brackets is 0. I replace this second term by this expression, and I replace the last term by the same expression. So I see that 0 is equal to twice b of psi of x, psi of y. Well, 2 can be removed, and I get the first out of infinite number of equations of this sort. Then I can go on, starting with this equation, applying psi to both sides, go on, go forth, and finally I get all possible expressions of this sort.
Oh.
Yeah.
Wouldn't you obtain
This,
the cases with p equaling to q? No.
yeah, I will obtain all possible choices of psi of p and q.
No, if you repeat this, you
Actually,
will obtain psi square, psi square.
No. Actually, I already have this equation. I have this equation.
Yes, of course. This is by definition. Yes.
So I now begin with this, and this. I have three equations where I have, so to say, square of x. Yes, so I'll obtain everything I need.
Yeah, okay.
Not only elements with equal powers of psi on both sides. As you see, this is pure algebraic construction. So it's very attractive, and one can hope that this construction can be transferred easily to the case of non-commutative algebras. And that's precisely the problem I'm going to talk about in the in the remaining part of my talk today. So let me finally formulate the problem. So the general problem is as follows. It's the most general problem I can think of, but it is as far from being solved as anything I know. Suppose you have a Poisson manifold M, and suppose you have a compatible Poisson structure. Then, according to the general deformation quantization theory, namely to the results by Casimir and others, for every such manifold, you have an associative product on the space of Homo power series in one Homo variable h bar with coefficients in the space of smooth functions on M. That's what they call the quantization of M. This quantization is essentially unique as long as you fix the class of the Poisson structure, but let us omit this. So this only asks for need pi. Now, when we have compatible structure, we have a commutative family of functions. In C infinity of M with respect to the Poisson bracket. Well, it is constructed as I explained. The question is, how can one extend this commutative family A from the Poisson commutative family to the space, the commutative subalgebra inside this Poisson, inside this deformation quantization from Poisson commutative to commutative in A, in quantization, in quantized algebra.
Star commutative, yes.
Yes, commutative with respect to the star product. Well, in this form, this problem will hardly be ever solved, I believe. At least at the present moment, nothing, or next to nothing, is known about the way you can quantize the bi-Hamiltonian structures. So 10 years ago, I was very enthusiastic about this, as all neophytes are, novices are in this area. But gradually, I started to dwindle, to shrink my hopes. First, I went from the general situation of bi-Hamiltonian structures, to these argument shift structures. Namely, we have mi, we have vector field psi, which verifies this condition. How do we quantize the corresponding algebra? The algebra generated by psi to the power p of the Casimir functions. I had high hopes for this because of that algebraic construction which I have just described. You see, it is well known, a well-known fact, which one can prove easily, that.
But the algebra is commutative.
Yes, I want to raise this algebra, which is Poisson commutative, the algebra spanned by these functions, to some commutative subalgebra inside this deformed or quantized algebra.
And star will be associated with pi.
Yes. I had high hopes for this because, it is easy to quantize the center. The Poisson center of there is an isomorphism of Poisson center of C infinity of m, which you extend by adding this form of power, and the usual center of the quantized algebra. Moreover, there is a very explicit way to go from Poisson center to the center of the quantized algebra. I don't want to go through these details because it will involve some work with what we call L-infinity maps and so on. But there is a very explicit way to associate to any Casimir function here a central element in this quantized algebra. Very explicit. So I hoped that one can somehow modify this construction.
You mean
Yeah.
in general or in the case?
In general.
In general.
In general. In general, not even in the case of. So when I was 10 years ago, when I started thinking about this, I thought it would be possible to do this in general. You see, and this construction actually holds in general, very explicit construction. So I hope we can construct some linear endomorphism psi hat of linear endomorphism of the quantized algebra. Which would satisfy the same condition as psi does, but with respect to the bracket, the commutator. That is to say, psi applied to this commutator minus psi minus psi here twice will be equal to 0 when we do it twice, right? I spent some time working on this, and it realized that it is very hard to do, if at all possible. I don't want to go into details, but if you try to do this naively, so to say, if you try to construct this psi hat in an inductive way by adding new correction terms for every stage, you will very soon run into the situation where your equations turn cubic and not quadratic. And these cubic equations, they cannot be identified with anything, with any homological abstraction which I know of. So usually when people do such deformation quantization stuff, they construct maps inductively by degrees in h bar, and then every new stage is dictated by some homological abstraction. And in this case, homological abstractions.
Poisson homology of
No, it doesn't help. It doesn't help because you get cubic equations.
No. I mean that's quadratic abstractions.
Usually, well, in usual case, you get quadratic abstractions in Poisson cohomology, in Poisson, in Hochschild cohomology, and all stuff like this. But here, when you try to do something, you get some cubic equations which you cannot interpret. At least I wasn't able to interpret them as some homological abstractions. So pretty soon I realized that was too much to ask for. So I try to do this at least in the case of Lie algebra. Let now M be a very particular case, Lie algebra, G star, and psi be a constant vector field. In this case, the quantization is well known. The quantization of M is well known, and it is known that it is equivalent to the universal enveloping algebra. Right. So we begin with the universal enveloping algebra, and we look for a linear operator. Psi hat on UG, which would raise to UG the vector field from SG. And well, in the best case, you would assume that something
Gosh,
like this.
can you explain a little bit what do you mean by the word that the quantization is equivalent to?
Okay.
What does it mean?
Well, it's very simple. It is very simple. One can prove that when you begin with G star, equipped with the standard Kirillov constant Fourier Poisson structure, this is KKS structure, the linear structure. Then the quantization.
Somehow related to
It is.
formula.
It's actually. Well, it is related, but not very directly. I have never seen this done in terms of Campbell-Baker-Hausdorff formula, although it is definitely there. People prefer to speak about Poisson-Grabber-Hopf theorem, but whatever thing they use, whatever construction they use, the outcome is as follows. The quantization can be restricted to SG, which you enhance by adding H bar, so to say, get only polynomial coefficients in all by differential operators, which they appear, right? Moreover, it is essentially unique. Essentially means up to an equivalence. Unique. And since every element, every pair of elements F, G in SG to a finite sum of the form I from 1 to some capital N, H bar to the power I, B I of Fg. So there will always be a finite sum. The top degree actually would depend on the top degree of F and G, but the sum will always be finite. Hence, one can conclude that one can set H bar to equal to 1, and we obtain a well-defined product on SG. So we can set this and get a well-defined product just here, because all the sums will be finite. So we will, beginning with polynomial functions, with two polynomial functions, we get just another polynomial function, right? And then it is almost immediate. You just check that the universal properties holds, which allows you to get a homomorphism from UG to this algebra, G star. And due to the Poisson-Grabber-Hopf theorem, this will be always an isomorphism. You see? So it is not canonical.
Isomorphism of associative algebra.
Yes, isomorphism of associative.
Isomorphism.
It will be homomorphism, but it will be onto, and the dimensions will be the same in all degrees. So get an isomorphism.
And the natural.
It's not very natural, as you know from the theory of the flow isomorphism. The flow isomorphism is, I mean, you can always take some self-isomorphism inside here and inside here. And it's not very natural. It actually depends on what you begin with, but there will always be an isomorphism.
I mean, is it functorial or not?
What do you mean functorial?
Well, if I have a morphism of algebras.
Of Lie algebras? Oh, very good question. A very good question. As far as the functoriality of deformation quantization is concerned, I think it is still an open problem. Probably in this case, this problem has been solved, but in general case, I've seen people working on this pretty intensively. well, some 10 years ago. Maybe they have done something since then.
Mm-hmm.
Yeah. Okay, so I just cut down my expectations a little bit. I just wanted to get a map psi hat on UG, raising psi from SG. In the best case, I expected that psi hat would still satisfy some kind of equation similar to this equation, the psi hat square applied to the star product should be vanish, whatever it means. But well, I spent some time working on this in this setting as well. But eventually I ran into Pavel Saponov, who showed me the construction of quasi-derivatives, which he shared, which he introduced jointly with Dmitry Gurevich. So Gurevich and Saponov introduced what they call quasi-derivatives. And also Pavel Platov was also there.
Bosch, what do you mean by this notation? Action, action psi on the star.
Well, something like, actually I didn't know what to do. I just wanted to have some something similar to what I began with, something like.
You will explain.
Yeah, I expected that I was going to find something which would verify the condition that psi of f star g minus psi of f star g minus f star psi of g psi f.
So you need a good definition
yes.
of a symmetry for.
Yes.
For
I expected to get this, but it turned out to be a bit less promising than I expected, but still I get something. And it was due to my acquaintance with my acquaintance with Pavel Saponov and Dmitry Gurevich, who showed me the construction of quasi-derivatives. Their construction was initially introduced only in the case of the algebra GLN, so I'll give the construction in the form which they first introduced it to me.
Please let us write Gurevich's name in a good way. Something strange.
Gurevich. Yes. Here's the definition. Let G be equal to GLN. When there exists a unique set of operators, of linear operators, set of linear operators on UGLN, which satisfy the following set of axioms. Well, first, just quite forgot to introduce the annotation. They're denoted by D hat IJ. IJ run from 1 to n. So D hat IJ kill the scalars. D hat IJ, when applied to the generators EPQ, satisfy the condition. They give you delta function, delta IQ, delta JP. And 3, most importantly, they satisfy the so-called twisted Leibniz rule. D hat IJ of f times g is equal to D hat IJ of f times g plus d hat ij, sorry, plus f d hat ij g plus sum over k d hat, or probably minus d hat jk of f d hat ki of g.
They operators of the universal.
Yes. It is easy to see that these such operators exist and are unique. To see that they exist, you just check that they use induction to show to extend them to the tensor algebra of GLN, right? And then check that these extensions kill the ideal. Check that these extensions kill the ideal. Okay.
Kills or preserves?
Well, I mean, whatever. Preserve, whatever you prefer. They actually kill the generating relations. Actually, you can show that dij, when you apply it to E, PQ, and E, well, AB, ECD minus ECD and EAB minus whatever this delta AD ECD minus delta CD EAD, and this is equal to 0.
This is straightforward check.
Straightforward check, just very simple. So when I saw it, I immediately asked Pavel Saponov to check if this construction actually sends commuting central elements in UGLN to central elements, to the commuting elements. And he, on my request, he did some computations, and then he said, yeah, in all instances which he managed to compute, the commutativity was true. Commutativity held. So I tried to prove this in full generality. It took me a couple of years to do so. Maybe I was not very experienced in this. Maybe I would have done this sooner if I were more experienced in the area of universal and developing algebra. The proof which I finally came up with, and which we published jointly with my PhD student Y.Ikeda, was relied on the following observation, set of theorems. First, claim number 1. Let A sub psi in SGLN, actually in SG, be an argument shift algebra. That is the algebra generated by the iterated derivatives in direction of P of psi of central elements. Central in the Poisson sense element, right? Then there exists a head sub psi inside universal enveloping algebra of G, such that a head sub psi is a quantization of a sub psi, in the sense that when you identify the graded algebra associated with UG with symmetric algebra, this algebra is sent to a psi. You see, there is an identification of graded algebra of UG with SG. So when you take this subalgebra A hat sub psi and do this to it, you get A sub psi. So in this way, that's this statement was proved by various people. The question of whether such algebras exist was first asked by Ernest Bricevic Winberg in 1991. The question whether such algebras exist was asked in 1991 by Winberg. The existence problem was posed by Winberg. In 1991. The first solution was given by Nazarov and Olshansky. Who just constructed the algebra. They didn't construct constructed this algebra A psi using what they call twisted Yangians in 1996, I believe. Then there was a paper by Tarasov, but not the well-known Tarasov, but by some other guy with the same name, Tarasov, who was a disciple of Winberg at that time, who showed that if you take generators of this algebra, of this classical algebra, and just symmetrize them, symmetrization of generators, well, good generators, not all generators, but good generators in A psi, give you a head psi. Then in 2006, I believe, Lenya Rybnikov gave another solution based on the use of what we call Kac-Moody algebras and Hagen-Frankel center in them. He actually showed that such algebras, A hat sub psi, can be obtained by projections from the Hagen-Frankel center in Kac-Moody algebras on critical level, whatever it means.
We now speak about GLL
so this is true for all G, for all G. But as I told you, all these constructions only deal with the algebra, with A hat sub psi. So all these constructions give no clue of how the operator psi hat can be defined. They just say that this algebra can be raised to the universal enveloping. And usually this is done by considering certain generators of A psi and raising these generators to universal enveloping algebra. So this is done by very algebraic methods. You choose generators, you raise these generators, you check that these raised generators commute with each other, and then you say that now you can generate anything, and this will give you A hat psi. That's the first theorem, the existence theorem. Well, I don't mention many other papers here. So there were works by Dima Talalayev, who used Nazarov and Olshansky construction to define his quantum spectral curve. There were papers by Molev and his co-authors who gave explicit generators for A-hat sub-psi algebras in most classical cases. So, but none of these constructions gave any clue of how the operator psi can be raised to universal enveloping algebra. So all these constructions are purely algebraic. Then there was, so that was the first result, the existence result. It is very important for our proof, but it's not sufficient. The second fact which we need is again due to Lenard-Rybnikov and Wimberg. And the claim is as follows. If a hat psi exists, it is unique. Moreover, it is equal to the centralizer of certain set of elements in UGLN, in UG. Certain elements which they denote by T sub psi, Ti of psi. And in general, I don't want to describe them. They are described in terms of roots of the real algebra G and of the operator psi, and there are also some assumptions need to be made that need to be made. So I just described these elements in the case of G equal to GLN. So in case of G equal to GLN, these elements are as follows. Ti of psi. We can also assume that psi is diagonal. I mean, psi is an element of GLN star, so it is a matrix, and by a matrix, so I can assume that psi is diagonal. Using some conjugations, I can always choose a diagonal matrix as my shifting matrix. Almost all the time, this can be done for almost all psi's. So now this Ti of psi is as follows. We take the sum over all j not equal to I of the form Eij Eji and divide it by psi I minus psi j. We also need to add elements of the form Ei I from 1 to n. And now the claim is that if this algebra A hat sub psi exists, then it is equal to the centralizer of these elements. And since we know that this algebra exists, we conclude that the centralizer of this set of elements is commutative. Conclusion, which actually consists of just reversing the changing the roles of premises and conclusions of these statements. The centralizer of Ti psi is commutative. Now, let me give you a few, to just explain how the theorem I claimed, I formulated, was proved. The theorem is as follows. Theorem, and it's due to Yasushi and myself. Let psi be any matrix real or complex doesn't matter. N by N matrix. Consider the operator of psi hat on UGLN given by psi hat equal to the sum psi ij d hat ij. Then, for any f and g in the center of the universal enveloping algebra, psi hat p of f will commute with psi hat q of g for all non-negative p and q. The proof consists of checking that whenever they apply such iterative operator psi hat to elements from the center, we stay inside the centralizer of this set of elements. Just do it step by step inductively. The base of induction is clear because f and g are central, so they are in particular in the centralizer of anything. But then you check that if you apply the operator psi hat to element in the centralizer of the form of this form, then what you get will still be in the centralizer.
Just straightforward.
Just straightforward induction. Mm-hmm. There's no trick there. Mm-hmm. So I think that's almost all I wanted to say. Just let me conclude by setting a few questions which are still open and which are quite interesting.
Just a moment. Gosh, and for example, we have not GLN but SLN.
SLN is okay.
Works or not?
SLN is okay.
SLN is okay.
As far as SLN is concerned, we just
skip this.
Yes, because you can always add scalar matrices and there is no problem with it. Scalar matrices are good, but if you go from SLN to say SON,
yes,
then
it breaks.
Yeah, it breaks down. So let me formulate these questions and problems. It is so. This is part of my. This is a small part of my my thesis. So, but in case you wonder whether this is everything, but there are much more in the thesis which I totally omitted because it would take me too much time to speak about that. Also, all these constructions which I mentioned with this deformation, quantization, everything, I also also appear in the thesis. Okay, so this is just kind of most interesting part of it, in my opinion. Okay, questions? So first of all, you can define the operators d hat ij using different approaches. So let me give a few examples of how they can be defined. First, axiomatically, as I explained. Second, you can do the following trick. Take universal enveloping algebra UGLN and consider the following set of maps, sequence of maps. First, you co-multiply it, and get into UGLN squared. Then you apply the standard canonical representation to the left leg of your co-multiplication of your element, and identity to the right. You get to the matrices with coefficients in UGLN. After this, you multiply it by xi, whatever you get here, multiplied by xi, and take the trace. of a resulting matrix. You end in UGLN. Let us assume for a while that the trace of psi is equal to 0, of this matrix psi is equal to 0. Then this map is precisely psi hat.
The only question is what is rho?
It's the canonical representation which identifies GLN with n by n matrices. Yeah, canonical representation. Now you can do the same thing for arbitrary algebras and for arbitrary representations, and you check if this will give you something or not. We did this with Molev for, I think, G equal to SOM, and the representation which sends the Cartan subalgebra into diagonal matrix. There is a representation which sends standard Cartan subalgebra in SON to diagonal matrices. It's not the standard representation, but rather some more exotic, which corresponds to the anti-diagonal form of the orthogonal structure, right? Then it turned out that in this case, unfortunately, psi hat will not satisfy this condition. It will not send central elements to commuting elements for all central elements. But if you take a very particular set of central elements, the generators which come from the coefficients of the characteristic polynomial, and apply this construction to them, you'll still get commutative elements, commuting elements. This model did this by showing that what you get will coincide with his generators of the argument shift algebra in UGLN, in UG, in the universal enveloping algebra. But that's not the only way to define this map psi hat. There's another one, a third one, a more geometric one. Consider the matrix D of partial derivatives Dij on SGLN. So this is a matrix acting on SGLN. Consider the exponent of D. Subtract 1 multiplied by psi. So you get an operator from SG to SG matrices. Well, and take a trace, of course. Trace. From SG to SG. The claim
Psi again should be
just let me trace this. If I subtract 1, I think that if I subtract 1, I don't need to assume this, but yeah, I actually, if it's traceless, I don't need this one. This one will not show up if it's traceless. Okay, whatever. There's GLN, there's GLN. And the claim is that this is, again, if you take the symmetrization map to go from universal enveloping to SGLN, then take this map psi tilde, SGLN, and then symmetrization. Back to the GLN. What you get is precisely psi hat. So that's much more geometric. So this looks like the shift in the group. So maybe the correct construction would involve shifting the elements inside the group instead of shifting them inside the algebra. So I hope that I will be able to find the explicit description. One more, and probably the last construction which I'm going to mention. It is based on the interpretation of universal enveloping algebra. So this again can be done in arbitrary algebra. You see this shifting, this kind of shifting. I hope so. One more thing to go with the universal enveloping algebra. You identify UG. Okay, probably even UGLN with the left invariant differential operators on GLN. Left invariant, right? Then every differential operator psi, not necessarily left invariant, on GLN, can be written as sum of certain functions alpha on GLN. Tensor with elements x in UGLN, left invariant, right? Left invariant, x alpha. Let f finally be, or probably f capital, be an element in the center of UGLN. You interpret it as a bi-invariant differential operator and take the commutator of f and the function equal to the trace of the element in GLN. It is a differential operator, and you write it down as this: f alpha of g x alpha. Now I claim that if psi is invertible, if psi is in fact in GLN, then psi hat of f is equal to the sum f alpha psi x alpha. So we have a very geometric way to speak about this shifting. And again, it's rather shifting along the Lie group rather than along the Lie algebra. So I tried for some time to prove directly that this kind of shifting will send central elements to commuting elements in universal enveloping algebra. I failed so far, but I hope I'll be able to do this maybe by in some other way. That's all.
Okay, thanks a lot. Thank you.
I just promised to say something about the bridges with the previous. Just one thing I promised to do.
Yes.
I need to keep my promises. Okay, sorry. So last time I spoke about the Euler system, full symmetric Euler system on matrices of dimension n by n, right? So I explained that the chopping integrals can be obtained as follows. You take determinant of the generic matrix L minus lambda identity and differentiate it decay by where decay is a differential operator given by the upper right angle of the matrix. So you differentiate with respect to this element, the upper right angle, then with respect to the next element in the same antidiagonal, and so on and so forth. Right? So you do it k times, and that will give you decay. And 1n, d2, n minus 1, and so on. dx, xk, n minus k plus 1. Right? Mm-hmm. Now, if you want to raise this commutative algebra to universal enveloping algebra, we just replace this decay by d hat k. That's the d hat 1n, d hat 2n minus 1, and so on, d hat k n minus k plus 1. And that will give you the quantum chopping invariance. They will commute with each other because of this theorem which I mentioned here. By the way, this theorem can be proved independently of the general case. The fact that these elements commute can be proved independently of the general case of that theorem. You can prove this just by comparing the formulas with Tarasov's construction. That's all. So you can actually somehow quantize the full order system by replacing the usual partial derivatives by these quasi-derivatives of Platov and Safonov and Gurevich. Now that's all.
Okay, thank you very much. Questions, remarks? No question, no remark? Okay, thank you again, and we'll meet in a week in Zoom.
Okay.
Thank you, Gosha.
Thank you for inviting me. I hope people will at least ask me some questions.
Да.